Steingart. It's a pleasure to be here, and again, thank you for coming. I'm going to talk about batteries, but also generally what you can do with batteries potentially in textiles. And the point of this panel is to figure out how much energy we can store on the body, how much energy we can potentially generate through motion, through harvesting available light and potentially thermal gradients. Spoiler, not all that much, but some. and then what we can do with this. So I am not an expert in fashion, but I know a little bit about energy, and I'm hoping to interact with Amanda, John. Well, John may be an expert in fashion. I don't know. I know him to be an expert in electronics, but Amanda is, and I think many of you are. So it would be really great just to start a conversation here tonight about what you really need or what you envision the functionality of your computational clothing ought to be. So without further ado, that's John. That's Amanda. Here's a quote from sort of the nerd pope, Steve Wozniak, recently. And he says, I want the entire smartphone, the entire internet on my wrist. Now, whether or not you need this or not is irrelevant. This is a subjective need of someone who has some particular aesthetic want. And in this particular segment, he's complaining about the display. So I wanted to highlight sort of an important issue around both displays and about shrinking things, so we can take it back into textiles. And he's complaining that you can pack a lot of functionality into a watch, but it still has a little screen, and he wants a bigger screen. And somewhere else he says that he wants the screen to roll out into his wrist. So he wants an awful lot of functionality packed into a very small area. And the man has a very large watch right now. I don't know what kind of watch is it, but he's not a small guy, and his watch still jumps out. So there was this watch released just a few months back called the Samsung Galaxy Gear, and it's perhaps the first active smartwatch. They were probably scooped in functionality when you really boil down what this thing can do by the Microsoft smartwatch like 10 years ago, and then more recently by the Pebble. But you know, there's a reason for this, right? So this is a funny thing about this watch, and this is a really great picture of it, but on the Samsung website itself, this is what it says, right? So this is a review that was posted on the Samsung website. Samsung's first smartwatch looks really classy and has potential, but it lacks some really basic features, and its battery life isn't good enough either, emphasis mine. And it only works with one phone right now, and it's not worth 300 pounds. So this was on Samsung's website. So this was one of the more positive reviews. And I don't mean to take it out of Samsung. Well, that's a lot of fun. The idea here is to examine the difficulties in consolidating power, and then potentially what you can do with it if you expand it out over the entire body. So internet on your wrist is difficult. This thing has to piggyback off of a phone's internet, and it's still lackluster in terms of features. But we have the internet in our hand, right? And now I'm going to throw some numbers at you just to give you a little bit of context. It's got 5.5 watt-hours of battery life, and that's a meaningless number even to me, because you have to know what you're using it for. But a smartphone sets a good example of the duration. Even though this is a fuzzy metric, how long the battery lasts sets a good metric for how you use it. And there's some improvement to be had in these devices, but it's probably not going to be an order of magnitude. I'll probably be eating my hat with that at some point. But most of the power in this device goes to the radios and to the displays. And the battery accounts for 20% of the phone by volume, right? So that was less than I expected, actually, but think about shrinking this entire thing, getting the same functionality, particularly out of the radio, which is a real power hog, and it has to be all battery, and that's still not probably going to be good enough. And Steve Wozniak wants a bigger display. So there's this point where we're at cross purposes in trying to shrink down functionality and how much energy we can store in very small things. So I have this completely fudged plot where we're looking at battery life versus battery size, and not unsurprisingly, we have a linear improvement. But where things really begin to break down are when you examine what the display is doing. The radios effectively are all doing similar things, where we have to push more light to more pixels, and John can correct me on this, but generally when displays get bigger, they use more power. So if I overlay roughly the battery life versus battery size, we see immediately the fault of the Samsung Gear. They're trying to pack an awful lot of functionality into a very small device, and the reviews are really knocking its functionality. Right up front and high and center are these quantified self devices by Fitbit, Jawbone, and Nike, and they all roughly do the same thing. The Fitbit has an advantage, I believe, still over the Nike and the Jawbone in that it's wireless. But it has no display, and it's using one of these other devices that you're always looking at anyway to enable information. So it's already got an advantage over the smartwatch in the sense that it's assuming that you're going to use your phone to do something useful. This is something I just want you to keep in the back of your head. People are not going to probably give up their phones to use a shirt anytime soon. This is just my engineer's opinion of it. So replacing the functionality of a phone in a shirt may be kind of silly. So the thing about this is that as the battery size gets bigger, the battery life gets better, and you can do an awful lot with it. And shirts are relatively large compared to all of these devices. So in theory, your awesome shirt should be way up in the right-hand corner here. You should be able to do whatever you need to get done in a device, so long as you're not putting a massive display on it, and there are folks that have. I'm going to show you some of the things that my lab has done to put batteries into fabrics and talk about some of the technical challenges of getting that done. I don't think it's insurmountable. There are a couple of really hard things coming up, but I need to know from everyone here what exactly you want to do with it. So I'm just going to quickly touch on how energy can get into the batteries, assuming you're not plugging it in via USB or something else. John's going to talk a little bit more about this. I'm going to give you 2 slides on this. So there's been some press releases, if you follow these things, over wearable solar panels recently. Folks have been trying to harvest heat to do work for a while. There have been a number of watches. Watches seem to be a go-to point for fashionable technology that have been charged by body heat. They don't work very well. Vibrations have self-winding watches have been around for a long time and actually work quite well. To give you a sense of what needs to happen, I'm going to throw some more numbers out at you. And the important thing here is that these numbers are much smaller than what an iPhone needs, right? So an iPhone is a 5.5 watt-hour battery. And all of these things produce, at best, a 50th of 5 watts. So if a 5 watt-hour battery can run for 10 hours, then you need a nominal draw rate of 500 milliwatts. I'm sorry, for 10 hours. So the point here is that charging these devices or running them purely off of ambient energy is quite difficult. It's not to say that it's impossible if you strip the functionality down, but at best these are supplements to charging and things that you can boost up. Every once in a while, there's an effort to sort of take waste and turn it into energy. So there are a lot of efforts on, or not a lot of efforts, thankfully, but some efforts on excrement. People try to say, what can you do with it? And there's a number on this, and it turns out to be pretty low. And there's actually a paper published a couple weeks ago called "The Power of Glove" that was really just really quite bizarre, where they took a latex glove and filled it with urine and stuck some electrodes in it and called it a battery. And what's sort of fascinating about this paper are the keywords, and typing these keywords in any order, I think would put you on an NSA watch list. So it's a microbial fuel cell, natural rubber, power management system, urine, conductive latex, and energy harvesting. So it's an awfully. Well, the idea is that
not the first instinct.
Yeah, not
Once you let it mature.
Yeah. So we can talk about how much energy is in P during the discussion. So we can get into the details of why this is so difficult, but energy harvesting is hard to implement. You have to use batteries. That's sort of the thing to take away. You can gain a little bit of energy by moving around or by exposing to sun or by doing whatever. But in a practical application, and particularly an application that has unpredictable inputs and unpredictable uses, it's a difficult thing to run. So I'm going to throw a couple of terms around. Primary batteries mean batteries that are not rechargeable. It's primary because of the primary source of power. They're cheaper and they have higher capacities, and you can ask me after why that's the case. Secondary batteries simply mean rechargeable. They tend to be more expensive and they actually store less energy for reasons I'll get into. So here's why we can make batteries flexible, but to date it's been a challenge. And this is what the guts of a battery looked like. A battery, never mind what's up here, except for the fact that a battery needs 6 well-defined aspects, and it scales with size. So the ability for a battery to perform is effectively a direct function of your ability to maintain this structure and how big and its size. Unlike circuits, batteries don't get better when you make them smaller. It's an important thing. You can argue whether clothes get better when you make them smaller, but batteries certainly don't. What makes it hard to have a battery that's bendable is that these 6 layers are in constant flux, or at least 3 of the layers are in constant flux. And here's what I mean by that. What you see on the left is you're right, I'm sorry, is what a battery wants to do. This is an exaggerated example, but this is a battery that's charging and discharging, and you see it's changing an awful lot. So if a battery can choose its behavior, this is what it would want to do. The battery on the left is a battery that has no moving components and its motion is constrained. The battery on the left will last for, at most, 50 to 100 charge-discharge cycles, or at least that's what I was able to get out of it in my work as a graduate student. The battery on the right will last over 2,000 cycles, right? So the ability to charge and discharge a battery is directly related to how you account for this phenomenon. And the reason why there's billions of dollars put into battery research and you don't get anything out of it is that it's really dependent on the chemistry of the battery and the geometry of the battery. It's exceptionally complicated. The motion happens over multiple scales. So what you see here is just from atoms all the way up to millimeters. There's change happening. You have to account for it. So a lot of people tried to tackle this problem. There wasn't all that much interest in computational fashion or wearable electronics till a few years ago, so there hadn't been that dedicated an effort to it. But it came to a boiling point where a lot of people were asking my lab, what can be done? And by a lot of people, I mean enough such that I was able to get funding to do something. And I had a clever grad student, Abhinav, and he realized that just taking a page from concrete would help. So we made rebarred batteries. We used mesh reinforcement. So if you bend a normal battery, you get cracking along the points where you bend it. He simply took a piece of nylon mesh. This was meant for a bandage. We embedded a battery into the nylon mesh. It became very flexible. Here's the obligatory picture of a battery powering an LED. So what was interesting about this, and we didn't really think much about it, was that as we bent the battery, the performance of the battery actually improved, which was an interesting thing. Nylon mesh is expensive, so we redid it with a non-woven what you see is that we figured out why the mechanics work. So it turns out there's a couple good reasons why flexing the battery makes it better. We flex the battery over 1,000 times and it still works. And now we kind of made a meta battery that can power an Arduino and tell you what state it's in. So if it's bent, it tells you the battery's bent. If it's open, it tells you it's flat. The third thing we did is said, okay, well, this is all well and good, but it's not all that conformal. So how many of you know how spandex works? Okay, well, yeah, I know why you know why it works. So spandex is really amazing stuff because it doesn't really stretch, or it half stretches. The way it really works is that it's a bunch of fibers that are buckled precisely, and they're held together by little rubber bands. And when you pull it out, you unfold the fibers and stretch the rubber bands. So this is an exceptionally well-engineered material, and the fact that it's so cheap is a real testament to what you can do with weaving, which we were talking about just before. So I think there's a lot of room to push this even further. So we did the same trick, and we embedded a battery into it, and now we have a battery. So this is just, we're literally dyeing the fibers with the battery material. And we build a full cell out of it, and I dropped that picture, and we get 150% expansion. That's not supposed to be there. So the other thing we can do is simply make a high potential battery that's about 15 volts. So if the natural potential of the battery doesn't matter, we can you have a big enough area on a piece of cloth to put them in series like you would in an old boombox. You would have 6 D cells to get up to power. We can put 6 batteries in series to get to any potential, or N in series to get to any potential we need. So the final thing I'll show you tonight is some work that we did with Carrie May, and unfortunately the student that worked on this, Ala, couldn't be here tonight because she's ill. But we took these and tried to let Carrie guide us and encourage us to do something a little bit more interesting in terms of the shape and the design and functionality. So first, we took the process and tried to make batteries that simply were aesthetically pleasing. And we showed that the process can be cut into arbitrary shapes. So here is a triangle, and we simply take these triangular batteries and fit them to 3D printed tetrahedrons. And on the right-hand side, what you see is an actual feather, or the shape of a feather, and we can cut the batteries out in the shape of a feather, and we can impregnate the feather itself with the active battery material. So if you're careful about it and you match your chemicals correctly, you can insert a battery into anything. And the bigger the device is, the better the battery will be. So instead of having to worry about how much battery you can get into a small watch, if you can think of your entire shirt as fair game, there's a lot you can do. Batteries don't have to be big to be functional. Here, this is a prototype of a potential earring. So this is a wire that's coated with 2 batteries in series. This is a trick that we're patenting now for what that's worth. And we can power a fan from this battery, so that shows that it gives a pretty high current. And it's conformal to the piece of jewelry. So a coating on a piece of jewelry can be a functional battery. So what I've shown you is that we can make a battery of any shape and size, and this isn't rocket science. We just needed a reason to do it and some specifications on how it could behave. And these are easy to recharge, and I learned something by working with Carrie May, and that's for commercial clothing, you only have to be able to wash it about 50 times, which is surprising to most of my graduate students who have the same clothing for 5 years. So the same 3 shirts for 5 years. So the Frontier is washable, And this is a real trick, but I think there's some nifty things that can be done, because most of the chemistries that are used in cell phones, and if you're familiar with the concept of lithium ion, they're inherently not washable. They can never get wet. But that's not to say you can't make a battery that can get wet. You just have to give something up. Everything I've shown you here can be re-engineered to be washable, and this is sort of the frontier that we're working on. So I'm just kind of the cheerleader on this work, and I write the proposals. These are the folks that are responsible for most of this work. Abhinav on your left is a postdoc now looking for a reason to do more flexible batteries. So if you're in need of someone with this expertise, let me know. Ala is a student at CCNY who's hopefully joining my lab next year at Princeton. Ben Hertzberg is my postdoc, and Barry is another graduating PhD. So if you're interested in any of this stuff and are looking to hire PhDs in it, do let me know. And thank you. So unless there are any immediate questions on what I just spoke about, I'll pass it on to John. Abhinav worked really hard to come up with a configuration where the flex, you couldn't tell where it was flexed, because that's bad for the battery. But along the way, there are a lot of implementations that you could tell just by measuring the resistance. So we just overlaid one of those and then rigged up a very simple printed circuit that had something called a potential divider in it, and we had to calibrate it so that it had one resistance in one state and one resistance in another.
So does the resistance change?
And the resistance changes as a function of flex. Yeah, that's dead simple to make. It's probably, if you were making this and you wanted it for a bridge, there are better ways of doing it, but in terms of putting it into a piece of clothing, this is a pretty good way.
Cool. And does the resistance change during the battery life? Or?
No, it's independent.
That's really cool.
Yeah.
And the second question is about heating and then dangerosity.
So yeah, that's a good question. This is the same chemistry that's in a Duracell. So the electrolyte is a little bit caustic. It's like lye. It won't hurt you right away, but you have to wash it off. It's like that scene in Fight Club where they turn the fat into soap. That's basically what lye does. so you don't want it on your skin too long, but it's okay. We're working to get rid of that. But that's the only danger. It won't blow up. It won't catch fire. It's not like a Tesla.
So I'm at Columbia University, and my lab is called CLU, which is just a vague enough name that as we change what we do, it still remains somewhat relevant. And obviously, I'm very opinionated, so you can take everything with a grain of salt. Feel free to challenge me. But I'm going to speak a little bit about two things. The first is energy harvesting. Sometimes people call it energy scavenging. And when we look at wearable electronics in particular, we really have to distinguish between different modes of trying to capture energy. So the first mode, and the one that gives you probably the most power, is what I call people power. So this is like the wind-up flashlights, the kind that you shake, or with the knobs that you turn, things like that. And what's different about people power is you're getting somebody to do something that's exhausting, and you're getting them to exert themselves, but that means that a lot of energy is going in, and you're making a motion which can be optimized for generating power. And when we talk about fashion, clothing, embedded environment, this usually isn't what we're talking about. Maybe you could imagine, for example, making the stop on a door a little bit stiffer or something like that, but for sort of normal use, this is not what we're looking for. We're really looking for the next two things. The first is environmental power. And environmental power is power that doesn't come from the user, but comes from the environment. Photovoltaics, wind, things like that. And we'll see that that's actually a pretty significant source, and that's one that you should consider as a source of energy coming into wearable electronics. And the second is parasitic power, which is people power, but is people power in which you're not loading the user. Parasitic power, you're just shaving off a little bit or taking energy which you naturally want to take away and using it to do useful work. So I was very inspired by a paper that Thad Starner wrote in 1996, and he tallied up all the possible sources of energy. So a person, if you average, uses about 120 watts averaged over the day. A little less at night, a little more during the day. So what are we looking at? So your blood flow total energy involved in your blood flow is 1 watt. Breathing is also about 1 watt. Your body heat is 120 watts. And that sounds pretty good, right? So we heard, 5 amp hours, that's, you could easily power, all your friends' cell phone. But the Carnot efficiency between body temperature and a relatively cold room is only about 3%. So we're talking 4 watts, and that's 4 watts if you covered your entire body in cold harvester. So imagine dipping into a cold pool, head to toe, all the time. That's the experience to get just that 4 watts. So I wouldn't call it parasitic. It might be something you could use, but you'd notice. Upper limbs can exert about 60 watts, like pedaling or lifting, or people have talked about making a laptop powered by flexing forward. And then walking is also about the same. That's normal walking. Your legs can exert more power if you need them to, significantly more, but that's what walking is. So a long time ago, I'd worked on shoe power. And really the idea here was that a sneaker is there to waste energy. So the job of a sneaker is to act as a low-pass filter, to take the high-frequency bumps and jars and jumping and stepping, get rid of all the high-frequency components, throw those away, those get absorbed as heat in the foam, and then just give you the low frequency. So your foot still steps on the ground and stops, but it doesn't do it with all the vibration that then hurts your knees and does all that stuff. So this force displacement curve is really what you want out of a good sneaker. So you want some kind of viscoelastic material which then absorbs that energy. So if I made a shoe which just took that energy away and turned it into electricity, you wouldn't even notice. In fact, you'd thank me for it. It would be great. It would do what a sneaker does. Instead of wearing like wooden clogs, which are very elastic instead of very energy returning, and they don't do it. And so there's a paper that I wrote. This is actually the first paper I ever wrote. So I made 2 types of harvesters. So one used a piezoelectric polymer. And piezoelectric polymers are pretty interesting. I still work with them actually very extensively. But in the end, this is 16 layers of the material and really complicated mechanics. Walking, you get about a milliwatt out, which actually isn't that bad. You can do a lot with a milliwatt. We'll see how much in a minute. We also ripped apart one of those flashlights and put it on a shoe, and that gives you a lot more energy. It gives you about 100 milliwatts, but it gives you 100 milliwatts because you're now creating a lot more force and a lot more displacement, which then sort of harms. So this is people power. Let's forget this. This is parasitic power, and that's really what you want to go for. In terms of environmental energy, photovoltaics are a great way to go, and I'm always a little bit careful to not talk about them as solar cells. So photovoltaics take light and turn them into energy. Solar cells are specifically engineered to work with the sun. And the sun has a particular spectral range and a particular intensity. There's actually different engineering for outdoor photovoltaics, for space-based photovoltaics, and for indoor photovoltaics. But outdoor light has a very high intensity. It's free. And what's bad about it is it has a really broad spectrum. It has a lot of infrared light, and that's not good for efficiency. So the maximum efficiency you can get once you factor everything is about 35%. We can also think about harvesting indoor light. So in Western societies, we're indoors most of the day. In developing countries, people are outside for about 5 hours a day. In developed societies, they're outside for about 1 hour a day. Indoor light is free, maybe not. There's actually some debate there, depending on how you instrument the environment. But the spectrum of fluorescent lights and LED lights is much narrower, so you get a much higher possible efficiency, but the intensity is much lower. So we've done a lot of work looking at light availability indoors. And indoors and outdoors, you kind of see the same thing, which is that during the day, you have a lot more light than at night. And it's intermittent. And so we need batteries, we need stuff. If we're expecting the electronics to work all the time, we need something that smooths over the low times. But probably the most important thing here is that the scales are kind of different. So the top one is outdoors in Las Vegas, and that's just the sun. The middle one is a office, and the bottom one is in Times Square in the middle of the night. And what you see is that the axes have a 10 to the 4th difference. So 1 minute outdoors is harvesting an entire day inside. And so there's really not a lot of energy indoors. Our eyes are really good at adjusting to the relative brightness of the environment. We're not very good at telling absolute brightness, but the energy that's available indoors is relatively minimal. So we've done a lot of surveys, and if you're interested, you can download the surveys. We have a 1-year-long survey of 8 sites in 30-second intervals. And anyway, after all of that pain and suffering, we basically came down to the conclusion that this is how much energy is available. So in an indoor office with no windows, you're looking at 1.3 joules per centimeter squared per day, which is enough to support a very, very efficient communication data rate of 1.5 kilobits per second, which is really, really nothing. I mean, this would download a web page a day kind of level of data. Bright office is about 10 times that. Outdoors is 1,000 times that. So photovoltaics are great, but you have to think about the use scenario, where you're going to be, and deal with issues like the brightness and the intermittency. We've done some work measuring what this is, and we've built measurement units which can tell the difference between indoor light and outdoor light, which is kind of fun, and put them on people and all that. And then that data is also all available if you want to model it. And we've also looked at vibrational power. And vibrational power is interesting. If you've ever seen the flashlights that you shake, and there's a magnet inside and a coil, what you're doing there is you're making a mass spring system, and then you're moving the magnet past the coil. But it turns out that the mass spring system can have a certain degree of tuning based on how much loss you build into it. And there's an optimal tuning based on the frequency at which that vibration comes in. And if you look at people moving, we did a survey of people doing different activities. The frequencies at which those activities generate the most power is different. And so unfortunately, one energy harvester doesn't cover all applications. And if you make an energy harvester that's broadband, it doesn't harvest a lot of energy for any activities because you don't get that resonance. So in the end, walking and running wind up being the best. We tried all sorts of things like spinning in a chair, doesn't really do much. Opening the door and closing the door is even worse. But in the end, shaking something at a deterministic frequency and walking wind up being your best bet. So there is some energy available in vibrational energy, but again, we're talking really small numbers, comparable with what you'd get for indoor photovoltaics of about a credit card size. So there are a number of possible energy sources. None of them are super convenient, and all of them are intermittent, which is why you need to know Dan. So the last thing I want to speak about briefly is how we can use this energy. There are all sorts of electronics that we want to operate. We can talk about radios. Maybe it's a whole separate event. And there's a lot of great work in really, really low power radios, alternatives to radios, optical communication and ultrasonic communication, turns out, can also have some potential advantages. Sensors, we had a good question earlier about sensors, all that stuff. But there's some things that you can shrink and there's some things that you can't. And the 3 things that you really can't shrink are photovoltaics, because photovoltaics need to be large in order to harvest energy. The UI components, because we will not get smaller. We're a certain size, give or take. And this is one of the challenges with the watch. I had one of those great Microsoft Spot watches. And what was great about it is it didn't try to do too much. It only had 4 buttons, and it did everything with those 4 buttons. Whereas the touchscreen, more modern smartwatches, everyone's disappointed that the UI just doesn't get it. And that's always a challenge. And the last is a display. In a direct view display, you want the display to be a reasonable size, and they're just not going to shrink down. So, one solution there is really to think about printed electronics. And there's been an incredible amount of work printing things, and you can print almost anything. The printed version is never going to be as good as the optimized other version, but you can print solar cells, you can print batteries, and Dan is really the world expert in that. OLEDs, you can print different types of displays. Anything you can imagine, you can print at least an okay version of it. And this allows you to use almost anything as a substrate, including cloth, treated cloth, plastic, fibers, woven fibers, things like that. And so, thin film electronics, which is the field of electronics that deals with this type of deposition of active devices on substrates, is a really flexible toolbox. And what's great is whenever you have an idea, you can reach into the toolbox and grab what you need. And so if, for example, you want to make a microphone, you can grab a piezoelectric element, you can grab some transistors, put those together, and you have a microphone. If the next day you want to make a camera, you can get photodetector, you always need transistors. Get some transistors, you put those together. If you want to make an energy harvester, you can get solar cell and filters and whatever else it is. So, so this is what my group and lots of other groups work on, trying to make interesting new systems that take advantage of these technologies. And some of these are relatively straightforward to make. So one that we've developed into a usable kit is making electroluminescent lamps, and they're really easy to make. We did this as a TEI workshop a couple years ago, and TEI is a conference. This was actually at the Media Lab at MIT. It was hosted there, and so we had a bunch of folks that didn't know anything about electronics. I took them for about 2 hours about displays and electronics, and don't try to touch the front part of the soldering iron. And it's great, and nobody had any trouble with it, and they all got it to work. And it was a lot of fun. And you know, in the end, it's all screen printing. It's pretty simple, and even industrially, it's pretty simple. It's just there's a lot of mystique about where the materials come from and all that. And one of my students developed the kit and distributed the kit, and I was very happy to see this on the internet when I was looking for pictures, because his pictures are terrible, but his pictures are very nice. And so that's really one of many possibilities. But it's a light emitter. You can really put it on anything. People put it on cloth. Actually, somebody put it on a shirt during this workshop just spontaneously because they thought it was so cool. Like, why do I have to use this plastic? You don't have to use this plastic. We just brought plastic because, I don't know, that's what we always use. That's always an option. It's also possible to add interaction pretty easily. So I spoke earlier about piezoelectrics, and piezoelectric polymers are really nice. They're like saran wrap, but when you push on them, they generate charge, and that charge is relatively easily amplified and sensed. And so we did another TEI workshop in which we made OLEDs, and for these we developed the form of OLED which can be printed and made using essentially Q-tips and paintbrushes. Oh, thank you. And we wanted to make something that's a little bit interactive, so we added strips of this piezoelectric film, which we could screen print the electrodes onto, and then that all fed into the microcontroller and was able to give some significant interaction. So the lights and the user interface was all customizable, and then we asked everybody who's participating in the workshop, what do you want to make? And somebody made like a Simon kind of game, and other people wanted to make like a little keyboard that sang songs. And it's cool, and you could just sit there, cut it out with scissors, screen print it, and make it go. And the real key there is you're not firing piezos. This is all relatively lightweight material, and it's stuff that you can work with at home. And we also were very fortunate to have a small collaboration with Mr. Kim, who showed us how to make transistors using the MakerBot, and we showed that at Boticon 0, which unfortunately has not been succeeded by a Boticon 1. Which is something we should try to remedy. But that's another conversation. And so it's possible to make transistors. And again, all of this is relatively straightforward once you understand the technologies that underlie printing and printed electronics. So, if I have any conclusions, they're really that, it makes sense to measure everything so that you don't get going in a direction that doesn't make sense. So Dan joked earlier, and it wasn't a joke, that the thermal harvesting just isn't going to go anywhere. And once you look at the thermodynamics, there just isn't a lot of energy there. So what makes sense? What makes sense is gross mechanical motion and photovoltaics. Those are the low-hanging fruit, and that's what you should think about when you want to get parasitic types of power operating. It also really makes sense to test everything. There are a lot of assumptions that you can come into. We have a large collaboration in energy harvesting that I participate in. And we looked up in some architectural manuals, what the illumination indoors is, and I don't know what era they were from, but the incredibly high fluxes were specified for minimum office illumination. We were shocked to see that our offices were totally out of spec, and everyone is. So it's worth testing stuff. And Dan said this as well. There's really much more technology available than good ideas out there to pursue. And so, there's really the need for application pull, and there are a lot of folks who are able to develop components, but integrating them into something which is interesting and makes sense is really the next frontier for this. I can tell you 20 different ways to make thin film transistors using organic semiconductors. What I haven't figured out is the billion-dollar business that uses them, and that's really the next step. So, some things are harder than they seem, and a lot of things wind up being easier than they seem. There are different modes of what we'll call printing. So certainly screen printing is really easy, and that you can set up anywhere. And when we set up outreach, our lab is very close, so you can always come visit us at Columbia. But screen printing is a great mode for artists to work with because many are familiar with it, but also has almost no capital cost and it works quite well. There's some downsides to screen printing. If you need high spatial resolution, Getting it is complicated. It's not impossible, but it involves much more work, much more trouble than it's worth in many cases. Inkjet printing is a lot more complicated, but you can now get $130 inkjet printers with blank cartridges that you can fill, and that's another route to getting active materials. And then Dan turned us on to this concept. We've been doing a lot of work with what we call capillary draw printing, which is basically using a robot together with a pneumatic dispenser to put down lines. That's very inexpensive and really straightforward. And that's sort of how we did the MakerBot RepRap transistors. It's also possible to use a capillary pen. That wound up being a little more complicated, but we saw somebody follow on to our other paper at MRS.
Oh, cool.
And they just went to an art store, bought a blank paintbrush, like calligraphy, Korean calligraphy paintbrush type thing, squirted some semiconductor in it, and then mounted it on a plotter.
So it's really great to be here because it's not very often that I get to be on a panel where I'm completely out-teched, which is, especially in a gallery, this is awesome. So, and you guys just said all the tech backup and explanation for all of my sort of naive findings in the art and design realm. So this is great. So you guys just backed up everything already. So I'll just run through the designs. So I am currently in the Columbia University Department of Architecture. I teach classes around bodycraft, biomaterials, not directly architecture, but sort of technology, materiality, biology, and the body. I run a studio in Brooklyn called Skinteractive that covers everything from sort of structural engineering for couture, working on consulting with wearable electronics companies, all the quantified self type things, work with performance companies. I did a body sensor network for the Olympics last year with Elizabeth Strab, and then doing my own sort of R&D work within the space. I have a collaboration with a company in London called Bare Conductive, where we're working on an organic conductive ink, and I'm trying to feed it to slime molds to have them grow conductive traces into cotton. So, all over the board, really, this is my consulting work. I'm also the founder of an algae biofuels company, the co-founder, which we have a licensed technology to optimize photosynthesis for growing algae as a biofuel. So I have a whole other life in the energy space. I'm occasionally curate shows specifically around art and science. I have a background in science museums, very specifically. This is a recent show at the New York Hall of Science. And then I've just recently become the director of research and development at a new fashion incubator called Manufacture New York, which is a hybrid space that has studio space for independent designers, a full on-the-floor factory, and then I'm now in charge of what's called the Tech Annex, which combines advanced digital fabrication for textiles, so 3D printing, laser cutting, looms, et cetera, with a wearable electronics lab and a bio lab. So kind of putting all those things together, what kinds of things can we make, and hopefully bringing access to the kinds of things that you guys were talking about into a space that's more public and where fashion designers working can have direct access to these kinds of things. So that's just getting set up. We have a small space in the garment district right now. We're going to be launching in Brooklyn in the spring. And then here, the classes I teach at Columbia are more kind of high concept, what is the future of thinking about fashion? So before coming to New York, I was at the Media Lab for 6 years doing a PhD, and my work looked kind of like this. It was all over the board. I was focused on self-programmable modular robotics with smart materials. I did large-scale installation work, et cetera, and some fashion, mostly because I was always kind of just interested in fashion, and I'd sewn for a very long time. My final thesis project was making a robotic mesh textile that was programmable by demonstration. But while I was there, I was working on these fun fashion projects, as were sort of a few people in the lab. And what was interesting was it was this very strange time. I got there in 2003, and a lot of the work that was super technical the only way I can describe it is as if a computer threw up on your body, right? It was just like, let's just turn it inside out and strap it down and then it's wearable? No. So, well, yes, and amazing technologies. The sort of smaller versions didn't exist, but in the context of what does it mean to be wearable, and from a kind of the essence of what fashion design is, it was just not doing that. And there was a lot of tension between the traditional fashion world and what was being called wearable electronics. So at the time in the Media Lab, we got together kind of a group of us, some people from Harvard, from Parsons, from RISD, just kind of our network, and through our own little computational couture fashion show called Seamless, and this was wildly successful. This was like sort of this idea whose time had come. We had I literally think we had a $300 budget. We had an AstroTurf runway in the base of the Media Lab, and we had it up on the cover of ID magazine. It was kind of this weird, okay, this is the thing. So I went on to curate more and more of these computational couture shows because I was fascinated in what artists and designers could do with this as a medium. So let's try to learn from, as I was, all the sort of super techie people like you guys who were around the Media Lab, and turn it into different kinds of design prototypes which embody concepts that the public really relates to, either conceptually or functionally or just in terms of beauty and aesthetics. And so I went on and did a whole series at the Boston Museum of Science on Seamless, and then a series at SIGGRAPH, which is a computer science conference called Unravel. And what was so fascinating, we had these incredible devices and high concepts around performance, and a lot of talk about mobility and being out in the street and all this kind of stuff. But what was really funny is before the beginning of the runway show, every single time, every designer and their model was like, they're gathered around the power strips. It got to be this like kind of joke that I had to bring like 20 power strips, so everybody had to charge up their stuff. And it was like, how mobile are you? Well, can you make it down the runway? So I kind of got really interested in this space of energy and the sort of absurdity of what we were really trying to do, and how that was absolutely the limiting factor for so many of these ideas. So I think that, conceptually, the way that most people think about energy is like, we're kind of down here. And, I teach a class on bioenergy at Columbia sometimes from an architectural point of view. And everyone sort of thinks about energy as being defined as the outlet. And you talk to kids and, et cetera. So what is this? So this is, maybe people know to that point mostly. And there's not a lot of ways for us to understand and access where is our energy actually coming from. Knowing is it wind? Are we burning coal? You can't make any sort of decisions around it, and it's completely invisible and it's intangible to us. And so, just sort of thinking through this conceptually from a design perspective, there's a project which I much admire called Energy Futures from Dunn and Raby, two conceptual designers who run a program at the Royal College of Art in London, and they were thinking, hey, well, what if you feed hamsters to your TV? That's a different, like, energy is not just, electricity, like the body is energy, that food is energy. And so if we take a more kind of human-centric point of view around energy, what does it mean to sort of think about different jumping off points and putting the body and the human in the center? And are there different kind of paths and directions? So I was doing a sort of side projects, what we call them submarine projects as PhD students. And I'm sure you guys know this, all the stuff that your students are doing that you don't know about. And so, I was like interested in this space. So what is our personal relationship with energy? So being completely naive about really energy harvesting or anything in general, I just kind of jumped in and made my first project, which was called Piezing, which is a piezoelectric dress. And I'm so glad you just explained everything about how about how piezoelectrics works. I don't have to, but it was a dress that was sort of had these discs, which were a kind of harder material, and then piezoelectric film, which had just come out, which was much softer but created much less energy. And so the idea being that piezoelectrics are generally used in speaker systems, which is how I had used them, to basically you put a voltage in, they vibrate, they make sound. I was going to use them backwards. We'll vibrate them on the body, and then we'll save the energy. So just started looking at, how much can we make, and I had this little, I forgot to put in the video of the test circuit, but I did, I could shake it around and the LED would turn on, which was like, all right, it works. And then what was kind of more interesting to me was, my background before the Media Lab was in mechanical engineering, so really kind of fascinated with the kind of how do you deconstruct the body as a mechanical organism. And by the way, these are all charging this was all wired up to charge one centralized cell. And I think one of the most fascinating things about this was that everybody kept asking me, oh, so you're collecting energy, so the dress lights up? And I was like, no, you're not getting it. The whole point is to save the energy, to charge something else that's useful. But no one wants their dress to light up. I never want my dress to light up. Anyways, that's a whole other question about the wearable technology. But what was fascinating to me was I started looking around at research in this space, and Dava Newman, who's a professor at MIT working on a new biosuit for space, was sort of thinking about this paradox, which piezoelectric film and fibers now, they don't stretch. And so you want to be using them around all of the joints of the body where you want the stretch, right? And so then the closer that the harder they're tied down, the more vibration you'll get, but then the person can't move. So you're like, there's this like paradox there. So she was looking back, I looked through her papers at this research called the lines of non-extension from the 70s. It was like, how do you create like a mapping across the body, a three-dimensional mapping of all the places where you can have a rigid fiber, and still have the body move. And then so my kind of inspiration of the future of this piece and the way that I wanted to talk about it as a concept was to take something like a sort of piezo nanofibers, which these are two researchers at Georgia Tech, and apply that into a kind of three-dimensional weaving pattern. So this was a kind of where, from a conceptual point of view, then suddenly this dress makes sense, because in the version that I had, it was kind of like walk 5 miles, have like 0.1, volts maybe, right? And it's like, I never quite did the whole kind of calculation in the dress, but I did have the separate elements, which conceptually you could show that this was a material that can create energy. I did get like a couple of volts after many wears of the dress. But anyways, what happened was after this was sort of around in a couple of shows, and I got contacted by a choreographer in Paris, Prue Lang, and she had been a principal dancer with Bill Forsyth, who's a huge kind of European dance company, and she was sort of going out on her own and doing very interesting kind of contemporary French dance, avant-garde. I learned so much about dance from her. And she wanted to she was also interested in the sort of energy and the mechanics of the body. She wanted to try to make a completely sustainable dance performance, which means that all the energy for the lights and sound of the show were generated from the dancers' movements, and that she could actually choreograph this around what we needed. And so we met, I was in Europe, whatever, we met a couple times and started sort of thinking through how this would work. And what was really fascinating to me, also as someone who had worked between art and science a lot, it was one of the purest experiences I had where the art and the science were literally informing each other. So what we did was, I'll just show you a couple of these are just some stills from the show. There's a whole choreography sequence around these macaroons on the ground. So basically, the dancers would, they'd eat, and then they'd dance, and then they'd move, and then they would basically trade off their energy. So it's kind of, there's a narrative that's a lot more conceptually complicated from a kind of artistic point of view, but just to understand how the performance worked. And the grid sort of shrunk as the performance went on, and we had a matching LED grid above that would then shrink in terms of like focus. But here's just a couple of stills. But what we literally did was, first I did a couple of tests, like what are the potential ways that we can actually make energy, and I was like, okay, we're not using this piezoelectric stuff, it's not gonna, I can't get enough of anything. So I literally went back to the shake flashlight, like you said, massive people movements, and some flexible solar that also collected energy from the inside, and then backdriving separate motors, which, so you're creating basically electromechanical charge. So very big movements, but this is a dance performance, and so we're very lucky to be, this is the whole point of it, was to choreograph around what we needed. So I made some stuff, spent a week with them in the dance studio, just literally taping this stuff onto them, just sort of duct taping, see how stuff works, have them dance for 10 minutes, run a test, are we getting anything? So it was incredibly iterative and completely trial and error based, and which was really fascinating to me, like, of the whole process. So what we ended up with for the final costumes were 3 systems, one which was this track roller system, these just, stepper motor, and storing into a small lithium polymer battery, something that basically that's a sliding magnet, it works like a shake flashlight, and we could put these in all across the arms and legs and have particular dancing. Like, that was actually the best we were getting. It was like we hit that frequency. I didn't need to know what it was, but the dancers knew intuitively in their body. That was where we were getting their biggest surge. And then some flexible solar across the costumes just to kind of boost. We were recollecting the energy that we were generating from the rest of it. And then the way the system worked is that there was an exercise bicycle, which was also part of the performance. They were in this rotation, and so that was direct power to the LEDs, and then what we were getting off the bodies was exchange power, battery power, into the sound system. And a huge part of making this work was also finding the lowest functioning sound system, lowest power sound system that you possibly could have. So the sound was pretty bad, and on purpose. But you know, that's what can we run? We were literally going back to like, does anybody have a Walkman from the '80s? You know, these kind of things. Like we don't need like very, very minimal amplification. Anyway, so a couple of the modules, here's kind of what they looked like inside as I was making them. And I had all these plans to cover them very intricately, and the designers, the Prue saw them, and she was like, no, we're keeping them exposed. And I was like, okay. So here's the first prototypes, and then this was the kind of final costume. So there's track rollers, and it was all based, the positioning on the body was based on how the choreography worked and moved, and you know, the whole, there's all these other questions about hard soft, especially with these kinds of modules, but that's what's so exciting about what you're doing is putting the actual battery into something like a feather where suddenly the thing flexes, and that, you know, this was we were not trying to develop that, it wasn't the point of the project or the budget, but in a sense that does become the essence of making something wearable to me. But also, I mean, this was also fun because they did become these little appendages, right? So this was almost like something like she would play on her hip, and other people would play, you know. So it actually became a huge part of the performance, these, like they were performing with these sort of body objects. So I'll just, hang on, there's just a few more stills here. And then I'll just show a quick clip of the performance. A second here. Sorry, it was really low light in there, so the video's like quite grainy. And the whole idea was that it builds. You start out very slow with very little energy. The person's manically biking. And as they start eating more, the movements get much faster, and then you start to actually get much quicker movements that generates onto itself. You can see the flashlight appendages in the arms, and when you're there, some parts of the video you can hear this beautiful clicking noise. They became part of the instrument. Actually, she took music out of some of the sequences on purpose. Like this part was. They just ended up in a spotlight that was motion controlled. So all the light had gone basically by the time they ate all the cookies, the macaroons as they were, because we were in Paris. When it traveled, they had German cookies in Germany, and it's all part of the theme. Anyway, so since then we took this to Ars Electronica, and then Prue has continued the project, and what's kind of interesting about it is she wanted to have this be part of a bigger idea about theater and to make a sustainability rider, because she had spent her life for sort of 20 years traveling the world with this dance company and thinking how crazy it was, how many people and stuff they were carting around from city to city, and so she was interested in all these kinds of local notions around how do you actually have more sustainable theater. So she made a rider about how far people could travel to be in the performance. But anyways, it ended up that it designed me out of the project because there was no way that I could be flying to Paris to work on it, which was fine. I had other things going on, but so we're still consulting. But I like that I managed to be part of something that I designed myself out of. But luckily, Graffiti Research Lab at France, who got their start here at Eyebeam, have taken over and are working on her next version, which she is going back to trying to make a pair of piezoelectric shoes, which is what she originally came to me with. So her new project is called Time Project. It just premiered last week in Paris. So I have very little info, and I have no video, but I have a couple pictures. But basically, it is looking at different notions of time concepts. So how do we experience time? How do we perceptually slow it up, speed it up? What are the sort of time measurements that are non-typical? Like one of the, and they have corresponding choreography. How long does it take to do one side of a Rubik's Cube? that's a sequence of time. And so here's just sort of thing. And then what it is a system of these shoes which have piezoelectric, which is what he was showing before, a kind of updated version, or just newer version. And I don't know the tech specs on any of this yet, but I mostly just know that the combined shoes for 1 hour of dance was equaling 1 minute of very bright light. So it is a sad, but it was working, you know. And the shoes, I think the most important thing about this whole project was the shoes had to be wearable for dancers to be very active. This is a very kind of fun, jovial kind of show. So they couldn't be encumbered by the technology that was in them, and they couldn't be sort of watching out and all those things. So these are just some of the sequences. So she did a lot of streetwear dance, as you could see from other stuff. And anyway, so that's it.